This is part 2 of a series on KNN. In this video, we will learn about the optimal k-value and decision boundary for KNN classification. This video was produced in Korean and translated into English. The audio was generated by AI, text-to-speech. In the last video, we looked at the basic algorithm for KNN classification and how to compute a distance matrix using array broadcasting. And we wrote some code to perform KNN classification using the distance matrix. In this video, we will look at the types of distances and data normalization. Also, let's look at the optimal k-value and decision boundary. And let's write code that determines the optimal k-value and performs KNN classification. Now let's look at the different types of distances used in KNN. There are several ways to measure the distance between 2 points. 3 typical distance measures are Manhattan distance, Euclidean distance, and Minkowski distance. Let's look at the figure below. There are 2 points P and Q on the x1, x2 plane. The point P is at -1, -1, and the point Q is at 3, 1. The Manhattan distance between 2 points is defined as the sum of the absolute differences of their coordinates. The formula to calculate Manhattan distance is as follows. In this figure, the distance along the x1 axis from -1 to 3 is 4. And the distance along the x2 axis from -1 to +1 is 2. So the Manhattan distance would be 4 plus 2, which is 6. The Euclidean distance between 2 points is defined as the length of the line segment between the 2 points. The formula to calculate Euclidean distance is as follows. This is the line segment between P and Q, and its length calculated by this formula is 4.47. The Minkowski distance is a generalization of the Manhattan and Euclidean distances. The formula for calculating the Minkowski distance of order P between 2 points is as follows. This is a method to measure the length of a straight or curved path between 2 points, depending on a chosen parameter P. If P is set to 1, it becomes Manhattan distance. And if P is set to 2, it becomes Euclidean distance. When P is 3, this distance is 4.16. If P is infinite, this becomes Chebyshev distance. Chebyshev distance is a special case of Minkowski distance and is defined as follows. Since this absolute value is 4, which is greater than this value, the Chebyshev distance is 4. When training a KNN model, we need to decide which distance best fits our data. This can be done through cross-validation. Next, let's look at data normalization. Data normalization is a process that adjusts the observations measured on different scales to a common scale. The most commonly used are min-max normalization and z-score normalization. Z-score normalization is also called standardization. Let's look at the data below. There are 2 features, and the scale of the feature values is very different. The scale of the x2 is much larger than that of the x1. In this case, even a small change in the x2 value will result in a large change in the distance. It is not a good idea to use this data as is to measure distance, as the x2 values have a much greater effect on distance. Therefore, data normalization is required at the data preprocessing stage. Min-max normalization transforms data by scaling values so that they fall between a predetermined minimum and maximum value, typically between 0 and 1. The min-max normalization formula is as follows. A and B are the desired minimum and maximum values, respectively, where I is the index of each data point, and K is the feature number. Let the minimum values of each feature be M1 and M2, and the maximum values be uppercase M1 and M2. We want to transform these feature values into new values between 0 and 1. That is, the A is 0 and the B is 1. Then this value is converted to this value, and this value is converted to this value. All data points are transformed in this way. Z-score normalization transforms data so that it has a mean of 0 and a standard deviation of 1. This process adjusts data values based on how far they deviate from the mean, measured in units of standard deviation. The Z-score normalization formula is as follows. We need the mean and standard deviation for each feature. Let the mean values of each feature be mu1 and mu2, and the standard deviation be sigma 1 and sigma 2, respectively. Then this value is converted to this value, and this value is converted to this value. When normalizing validation or test data, you need to find the min, max, mean, and standard deviation from the training data and apply them to the validation or test data. This is because test and validation data may change in the future. Next, let's look at the decision boundary depending on the value of K. A decision boundary is a surface that separates different classes in feature space for a classification problem. In 2 dimensions, it is a line, in 3 dimensions, it is a plane, and in higher dimensions, it is a hyperplane. Let's say we have a feature space with these training data points. And let's randomly generate a lot of test data points and plot them in this space. We then estimate the classes of these test data points. These data points will be classified as class 1. And these data points will be classified as class 2. And these data points will be classified as class 0. This will then reveal the boundary lines between the estimated classes. These are called decision boundaries. The decision boundary depends on the choice of K value in KNN. A smaller value of K considers fewer neighboring data points, which makes the decision boundary more complex and may lead to overfitting. This boundary perfectly separates the red and blue data points. The misclassification rate is 0. However, if K is 1, and if the data point we want to classify is located here, it will be classified as blue because it is close to this blue data point. It is probably wrong to classify it this way. This is because it makes more sense to classify it as red. A larger value of k considers more neighboring data points, which results in a smoother decision boundary and may lead to underfitting. For appropriate fitting, the optimal k value must be considered. The optimal value of k can be selected through cross-validation, which can prevent overfitting or underfitting and improve the performance of a model. Setting k to the square root of n could be a good choice as default, where n is the number of training data points. This is a rule of thumb. Next, let's write some code to find the optimal value of k and determine the decision boundary. Let's create a dataset we will use. It is very similar to the one we used in the previous video. This dataset contains 900 data points with 2 features. It consists of 3 clusters or 3 classes. If we plot these data points in 2-dimensional space, it looks like this. We then split this dataset into training data and test data. 80% of the dataset XY is used as training data, and the remaining 20% is used as test data. N is the number of training data points, which is 720. We performed z-score normalization on both training and test data. The feature values in this dataset have similar scales from -1 to +1, so there is no need to normalize them. But let's try this just for practice. Calculate the mean and standard deviation from the training data and apply them to the test data. Then we write a function that performs the KNN classification algorithm. This function contains the code we used in the previous video. The inputs to this function are training data, test data, and a k value. This function estimates the classes of the test data points based on the given k value. First, we generate a distance matrix using array broadcasting, as we did in the previous video. We used Euclidean distance. Setting p to 1 computes the Manhattan distance. Setting p to 3 computes the Minkowski distance of order 3. Next, for each test data point, we find the k nearest neighbors. Finally, we estimate and return the classes of the test data points via majority voting. Now let's compute the accuracy on the test data while changing k from 1 to 700 in increments of 10. We call the function KNN predict we just wrote above and use the model with the given k to predict the classes of the test data. Then we compute the accuracy of that model and store it in the accuracy list. Next, let's see how the accuracy changes as k changes. The results are as follows. The x-axis represents each k value, and the y-axis represents the accuracy. If k is too small, the accuracy is low, but as k increases, the accuracy gradually increases. This dotted line indicates the point where k is 27. This is calculated using this formula mentioned earlier. N is 720, the number of training data points. From this point on, the accuracy remains pretty constant until k reaches about 550. From this point on, we can see that the accuracy drops sharply. In this case, the point where k is 27 can be considered as the optimal k. As the test data changes, the optimal k may also change. Next, let's generate a lot of test data points and roughly determine the decision boundary. We use a uniform distribution to generate 1,000 test data points ranging from -0.5 to +1.5. And we normalize this test data using the z-score method. We applied the mean and standard deviation obtained from the training data. And then we call this function to predict the classes of this test data. K was set to the value calculated by this formula. Finally, we use the predicted classes of this test data to determine the decision boundary. The results are as follows. Yellow dots are training data points. The red circles are the test data points where the class was estimated to be 0. The blue circles are the test data points where the class was estimated to be 1. And the green circles are the test data points where the class was estimated to be 2. You can see that the same colors are grouped together. You can also see these 3 boundaries appearing. These boundaries separate the training data points like this. Let's run this code. We got the following results. So far, we have looked at how to find the optimal k value and how to determine the decision boundary. In the next video, we'll look at issues such as the curse of dimensionality, lazy learner.